Sarthak, can you hear me?
Yes, sir.
Can you see the screen?
Yes, sir.
Sarthak, listen to me. Now I'm talking about connected components. The idea behind that, suppose you have X star. Is itself connected? It's fine. If it is not, suppose it's not connected. Then question is that whether, suppose this is your X, whether you can have some partition of X such that each of them is connected. They are pairwise disjoint. Why we are interested in that? Because if you have this, if it is connected, it will be a nice situation. If itself is not connected, then you go for a partition of that. If you have this, then on each of the class partition thing, we'll do some analysis of topology, and then we'll all this information put together to get the total picture. That means you will be having here local pictures, and then out of local pictures, so that you can have a total picture. So that is the basic idea of component. So component in some sense, the maximal connected subset. That means if it is contained in another connected subset, it has to be the same thing. So that here I have given definition, page 4, that U is called a component or connected component. If you are only considering connected thing, then you can say that it is component. You don't need to use the adjective connected. If U is connected, and you see that U is connected, extra we are starting with this, U is connected. U is connected, again I recall, this means this is connected with the subspace topology. Okay, right? And suppose you have another thing, this V is also connected. Then U must be equal to V. This is called the component. Okay, so that if X star itself is connected, then there is only one component, basically X, if it is connected. Okay, so U is called connected component if U is maximal connected subset of X. Here, of course, maximality is with respect to the set inclusion. Okay. Now, look. That example says if X itself is connected, then X is the only connected component of X. On the other hand, if you have the discrete space, look, discrete space, suppose this is discrete. Then look, the components will be have to be points. You have to be 1.6. Anyway, first of all, any point, okay, if you take this, it's always connected. But in discrete space, only these are the connected sets, components. That means, because if you discrete space, if you take more than that, suppose A is subset of X, he has more than one point. Then A tau A, look, this is also discrete. If this is discrete, this will be also discrete. It is subscriptive also. Then A you can write like anything, like B union A minus B, where B is a proper subset of, then B is open here, this is also open here. So this will be disconnected. So in here, discrete space components will be only the points. Okay, right? And of course, you can think of that converse questions. You can try to answer that. The converse is true. Suppose, what is the converse I'm saying? Suppose the components in a topological space only the points, that one point exists, is now discrete. That you can think of. Next result, that theorem 6. This is very important about dealing with components. In fact, theorem 6 of that page 5 tells you everything about the components. Okay. The connected components are pairwise decision. The proof is very straightforward. That if you have two connected components, either you will have this or else look, if you have a point, since C, D are connected by a previous result, that are corollary to the chain, the corollary 3, I think, yes, that C union D will be also connected. C is a maximal connected set. So you will have this. That means C equal to, has to be this. That means D has to be equal to C. We change the roles, interchange the roles of C and D. That means you do this. It will imply. So you get C equal to. So basically corollary 3. Corollary 3 is very important. Okay. And similarly, already I have seen that if C is connected, then C bar is also connected. But this is a component, so it has to be this. So component has to be closed. Every connected subset of X is contained in a connected component. Okay. This thing, it can be proved many ways. I have given a proof there. Okay. So that you read the proof. This proof is very interesting. Okay. What way of doing it? That in C, that every connected subset. This is an important result. Every connected subset of X is contained in a component. Okay, so that what will do that? Basically, take a set C, connected subset C. Okay, then what you do? Basically, you take all these things. Look, C, D. I said with the family. Okay, I started with the D family connected subset instead of C. take this D. So take this at CD, you take all these families of the, basically first you take A subset of X is connected in X tau and a content T. All each of which contains T. Okay. So that here, if you take union of all these members, that means basically members of this A belongs to this. Then it's connected subset of that. You'll have to check this is connected. Look, its intersection, it at least contains A. Connected set by definition is non-empty. So that each of them, sorry, dot A, so D. Look, intersection of all these A contains D. So intersection is non-empty. Again, by corollary 3, this will be connected. Okay. Right. And obviously by definition, this is contained this. And you'll have to check this is maximal. Because you cannot have any other. Suppose you have another connected set containing this. Okay. Then he contains this, then he contains, look, this is empty, the D is also here. Each of this contains D, so this contains D. That means he is one of these members. So that he will be actually a subset of this. Any connected subset which contains this has to be a member of this because of this. So it has to be contained in this, so that it will be a component. Okay, this is the proof actually. And T is very easy, that since every subset is contained in a component, if you take any point X, then this is contained in a component. That component you call it Cx. Cx you call the component containing X. Then X will be, because X, it contains X. Okay. Look, here some components may be equal. For X may be equal. But otherwise there will be pairwise decision. But I only needed to show that X is the union of its connected components. Okay. Right. Look, I have proved that the component in a topological space need not be open, because I have proved a component, I have proved a component is closed by maximality, but it need not be open. And I have given an example of that. Okay, that component need not be open, components are closed. What? The next thing, this very important thing, is that path connectedness. See, last time I already told you, this is very important because actually it is not only algebraic topology, algebraic, it is also used in analysis. But analysis often path connectedness coincides with connectedness. Okay, so that will explain that. Though the notion of connectedness is very important in analysis and topology, its definition is somewhat negative in nature. Definition of connectedness provides for the non-existence of a certain kind of splitting the space. A more positive approach towards the same sort of problem is provided by path connectedness. Why it is a negative approach, why this is positive approach, that after you do study something about path connectedness, then you realize. Okay, now the path, so that first we need to define what is path. Okay, so I have given the precise definition. Suppose you have a topological space and you have 2 points here. Okay, first I'm doing 2 points. And then a path from x to y, a path. I've written a bit differently, but let me tell you that. Path from x to y is first a continuous function. This is the requirement, continuous function. F, this is obviously we have the usual topology. If you do not mention anything, this is the usual distance here. To x tau such that f0 equal to x and f1 equal to y. I am not saying they need to be distinct. Usually we take the distinct points because if you have not distinct, then you can take a constant function. That will give you always that. So that here in the path, people usually say the non-constant paths. The existence of that non-constant path. That means this continuous function is called a path from x to y. Look here, there is no, you don't need to worry about whether you will take 0 here or 1 here. It doesn't matter. Okay, you can interchange them. You can take f1 equal to x, f0 equal to y. Okay, that will tell you that path from y to x. From 0 to 1 we go. So that this is a path. Path by definition has to be a continuous function. Okay, we do not take any function. Okay, that I made a comment that actually you have the metric here. Okay, right? So that here actually this uniformly continuous. I don't know why I have written that. This is not correct. Because uniformly continuous function we define between two metric spaces. So if you take a metric space here, then this function actually will be uniformly continuous because this is compact. So that instead of topological space to take a metric space, then any path will actually uniformly continuous. And its image will be, that will be always true. This is compact and connected, so its image. Okay. This will be compact and connected. That is true for any topological space. But uniformly continuous function will define only between two metric spaces. So this comment should be only when x tau is a metric space you have that. Okay. Now this is a path, the continuous function from x to y. The way I have defined x equal to f0, y equal to f. Okay, but usually this from x to y. Now the definition I have given here for a path connected space, that if for each pair of points x to y belongs to, there is a path with endpoints x and y. f0, f1 are called the endpoints. Okay, that is there exists a continuous function that I explained that f0 equal to x, f1 equal to, then it is called path connected.